Kerstin, presenting additive manufacturing of glass, characterization of thermal and residual stresses.
Hello. So I will present something on additive manufacturing of glass, and I will focus on thermal and residual stresses there. So this is me, and my research topics are optical anisotropy effects in thermally tempered glass and additive manufacturing of glass. And I first want to start with the optical anisotropies here. I have 3 examples here. On the left, you can, so all of those buildings are at our TU Darmstadt campus. On the left, the building where we used to eat, and you can see a photo taken with polarized filters, and you can see a lot of dots, like a bit blue and orange, black and white. Oh. Okay. Back to the left picture, we can see blue and orange and white and black dots. This is a building around 1978. The middle one is actually our building where we have our offices, the ground floor. There you can see like cross the black and white lines in the sky. Below there are also those lines, but we cannot perceive them that well. And the right picture is a staircase in that building you can see in the middle picture. And actually on the beamer, it's very hard to see, but there are also white diagonal lines. And these effects are called optical anisotropy effects. You can see, like from left to right, the quality, so the optical quality of this product increased. And I want to tell you a bit about birefringence. So birefringence is the optical property of a material having a refractive index that depends on the polarization and propagation direction of light. So on the top, we can see a crystal that have different refractive indexes depending on the direction. And glass is an isotrope material, but it gets birefringent when applied to stresses. So when glass is applied to stresses, also it has this different propagation or this different refractive indexes. And below we can see here, this is actually acrylic glass. It's not glass. Within a 3-point banding test between 2 polarizing filters. And here, this is the stress optical law. So we have the retardation S, which can be mapped to those interference colors. On the right, we again see this 3-point banding test and the map of interference colors related to the retardations. And we can see that these interference colors depend on, of course, the light I use. If I use blue light, I only have blue lines here, but in this case, white light. And this depends on the photoelastic constant, which is a material constant, and the principal stresses, but the principal stresses perpendicular to the light path, and not the principal stresses itself, but they're different. And that integrated over the specimen thickness. So when we look at this product, we have thermally tempered glass, which gets cleaned, then heated up to roughly 620 degrees Celsius, and then gets cooled down fast. And at the end, so the aim is to have this parabolic stress profile over the thickness of the glass. And when we go back to W.AMCA's law, we now know that the retardation, so the interference colors, depend on the principal stress differences. So in this window, thermally tempered glass, there must be some principal stress differences. And so, oops, go back. This parabolic stress distribution should be symmetric if heating and cooling is completely homogeneous over the area of the glass. And it seems, so it's hard to have this completely homogeneous in a large oven, and also to have a homogeneous cooling when you cool down with air by nozzles. So that's where those interference colors come from. I did lots of research on how like these compression stresses on the surface can differ, and which compression zone depths and how do they differ. And then I saw these pictures from Additive Manufacturing. It's one of the first specimens Matthias and Robert did, and they connected borosilicate glass plate with the glass rod. And so on the left, you can see those specimens, and on the right, you can see those specimens pictures taken between polarized filters. And you can again see those interference colors. The colored one is before annealing, and the right picture is after annealing. You can still see some black shadows. I don't know exactly if this is still interference colors or not, or if it's just a shadow. So annealing is when you cool, so you heat up the whole product again and then cool down very slowly to reduce those stresses. This is what motivates me to do research on the residual and also the thermal stresses in additive manufacturing of glass. And my aim is to get a better understanding of fused glass deposition modeling. And I would like to describe the temperatures during the process, the thermal stresses during the process, and printing and cooling, and also the residual stresses which remain after printing. This is challenging because we have a temperature and time dependent material behavior, and we have very high process temperatures. And of course, we have numerous influencing variables. And here this picture shows a nice rendering of Robert. So we want to do fused glass deposition modeling. So we want to put glass filaments onto a base plate. And therefore, we have this machine under construction. On top of it, there's a melting kiln. Maybe I take the laser pointer. So this is our melting kiln, which you can see on the photo here above. We have a nozzle which goes down there. Actually, we cannot see the nozzle in the picture because it's too small, but we can see an extra heating for the nozzle. It might be too small for you to see it, but there's a little, you can see this little thing there. It's actually this high, but in this wall. Then we have a gas torch to additionally heat up the base plate. We have heating bed, which is here located, and in the picture here, and we have our XYZ control. Okay. The tools I want to use to investigate additive manufactured glass is, there's photoelastic methods. We have so we just bought a thermographic camera, which I want to use, and I want to use numerical simulation. The process steps I want to investigate is first just heating and cooling of the base plate, and second, a first line or first dot of filament on top of this heated base plate. The first step I split into 3 parts. First part just using the gas torch, second just using the heating bed, and the third part will be using heat bed plus gas torch. The second step is also divided in those two steps, just using the heat bed plus the glass filament from the top, and then additionally use the gas torch. So this first step, there are some first results available, and I want to show you the experiments here. So I have two students who are currently doing these experiments. On the left, we have the light and polarizing filters, which is in the photo back here. Then we have the gas torch. Unfortunately, the students did not take any picture during the experiment, so we have no picture of the experiment with the gas torch. And I also didn't think about it when I visited them. So we have the glass specimen in this schematic drawer, and here's the clamp to put the glass specimen. This is the second polarizing filters and our thermographic camera, and the other camera is just next to the person taking the picture. This is an example of the thermographic picture and the photoelastic picture. So this is a borosilicate glass, and you can see the gas torch. So in this thermographic picture, the emissivity of glass is not included. So these temperatures shown here are not the temperature which we expect for the glass surface. So just don't take the numbers from here. It's not the correct numbers. So those students did the calibration of the photoelastic setup and also the calibration of the emissivity of three types of glasses. They used borosilicate glass, soda lime glass, and quartz glass. And they did these experiments and numerical simulation. We have some nice fracture patterns, and I think it's very nice and also a big difference between those three glass types. These are fracture patterns from borosilicate glass, and we have specimens without any cracks. We have specimens with some cracks, and we have specimens, especially in borosilicate glass, which look like a little animal. And so we observed specimens that broke directly in the experiment, like this on the right side, that directly broke. And we have specimens that broke, like we guess it was until a week after the experiments, but we had only time to look at the glass specimens 4 weeks after the experiments, and those cracks grow. That's a typical aspect in glass. It's a, and so this specimen, for example, broke a lot time after the experiments. So that's why it's also important to look at the residual stresses which remain in the product after printing to prevent a fracture after installing. With soda lime glass, we also had different fracture patterns. We had glasses that didn't show any cracks. We had glasses that showed like super small cracks on the top surface where the gas torch has been. We had specimens that had a crack but didn't fall apart. And we had specimens that just fall into lots of pieces. The quartz glass didn't show any cracks. They are just very good to get all the heat, and they don't mind the heat. Yeah, further results are coming soon. The students have to hand in next month. So I'm very looking forward to get their results and everything collected. Yeah, do you have questions? Philip?
Of the graphic samples that you showed, that are set of it, would I always see the cracks that are used thermally, or do you also have the situation that you have micro cracks that are used thermally, but there's small to see and they only grow after a certain amount of time because of such pretty good crack growth?
So you're asking if there are cracks before the experiments in those glass?
Induced by the experiment, so small that I haven't seen.
Okay, so micro cracks induced by the experiments, but that's small that I cannot see them. I guess that's the case because for subcritical crack growing, you need this crack tip, which then grows. Yeah.
After a couple of hours, days, weeks, whatever the time period is.
Yeah.
So that would mean there's certain, like we have a stress field that you thermally, where we have, which is not strong enough to drive certain minimum size cracks, right? We kind of put at least, if you have a copy of the power formation of the West, you could get a copy of how short cracks need to be so they don't grow in this stress field.
Sorry again. I got lost. Okay.
If you do this, have an and how strong the temperature gradient is.
Yeah.
You could evaluate the thermal spread.
Kind of. Because I'm still missing some information. So I have my gas burner on the one side, and I'm looking from the other side on the glass specimen. Because when I look from the other side, I will see the gas burner and not all of the area. What the thermographic camera can see is the surface temperature of that side. That's why we don't see the gas burner in here, because you can just see that thing and it's kind of opaque for the thermographic camera. So I have this temperature field known, but not the other one. And there will be a distribution behind us. So we can, what the students do is the numerical simulation, and they can get this surface temperature really nicely and it fits good. But yeah, there's some unknown things. So I hope we can know the stress field and also know which stresses remain in the specimen to then maybe make a guess on the subcritical crack growth.
Okay, once you figure out the problem of determining the stress field, you can then introduce a crack, which might correct or rectangle arbitrary length and determine how short this crack needs to be to not grow. I feel like that's an interesting analysis to do, because we can figure out that it's possible that there are cracks so short where how short is in this case. I have no feelings because that is so brittle. So it could be incredible. But you have to manage how to set temperature. You also with the demand. Gas so this is also something you have to monitor. So the brain per se, all cracks are healed, but then in the moment I turn off the flame, my specimen goes down, I still have my temperature gradient and get into a regime where I might be growing. So the crack heating crack heating with the process that is very something we have
It's an interesting discussion. I like it.
Transfer this. My question is, what is your advice to that printer?
My advice to the glass printing team is repeat this experiment in our construction chamber.
How should they treat their advice? How should they say adjustable?
Well, adjusted in that way that those cracks don't grow. Yeah, and that should be an outcome of this research. But at the moment, I don't know which parameters do I have to adjust. And I guess it's a lot about cooling down slowly. This was in just in the laboratory, like you can see here. We were just in room temperature. It was high room temperature because it was just hot with all those kilns in that room, and the door wasn't opening very well. So maybe 30 degrees Celsius in that room, but the glass had up to 450 degrees Celsius. So we need to really do this experiment in our kiln, because that's a very totally different circumstances, because there we want to have around 500 degrees Celsius, and the glass needs to get up to 800, 900 degrees Celsius. So I'm at the moment, I'm not sure how these experiments are. So it's the first idea what happens, and it's nice to take the numerical model and show, like, try, can we map this, and then go to the very higher temperatures and see what's happening there.
And I think also an interesting issue, like say, we can wait 4 weeks here.
Well, I would say after 1 week, but we just got the idea to have a look again.
And then the next question would be, somehow speed up this so project of lead, but somehow mediate or whatever to make sure that the components are printed. This PhD Padua, you may remember it. They 18 years ago, they did the same investigation for the 3D print of glass on the MIT. That may be also interesting to evaluate what their results were. They actually come from a similar environment.
Yeah.
For what this to do.
That would be good.
Yeah.
Okay, thank you.
Thank you.